Hello, welcome to Math with Beth. And today we're going to do implicit differentiation and logarithmic differentiation. So let's take a look. So these are two different types of ways to find the derivative. So hopefully you're totally fine with just the normal methods, chain rule, product rule, all that stuff. So these are two different ways to do it, and there's a reason why you would use these. So you're not going to just randomly use these ways. So let me explain how and when you'll use them. So first, as a review, if I was just doing the regular derivative of something like this, if y is already by itself, this is just an explicit function of x because everything is in terms of x on this side. So to do the derivative, we would just say dy dx equals, and then we would do our normal power rule. Since this is really the same as x to the 1/3, we would put the 1/3 in front, subtract 1, and that's it. Technically, what you're doing at the end there is doing the derivative of x in terms of x, but dx over dx just equals 1. So that's why we never have to write that part. Well, what you're going to see today is since we're doing derivatives in terms of other letters, you will always have to add that extra part at the end. So this should be review. If it's not, I would definitely work on regular derivatives before you get into implicit differentiation. So now here's the new way to do it. So first of all, these are the same equation, right? Because I could have raised each side to the third power and it would turn into this. But now this is a case where we don't have the y all by itself, so I can use implicit differentiation, which just means I'm going to take the derivative of both sides of the problem in terms of x. So when you do that, if you're doing it with a y, you first do whatever you would normally do. So in this case, the power rule, but then you do have to add that extra step of the derivative of y being dy dx. On the right, since it's an x and we're doing it in terms of x, we would just do the normal thing and say the derivative of x is 1. So this is what you're going to hopefully get used to today, that anytime you're dealing with a y, you're going to have that extra step of multiplying by dy dx. So now we're just going to get this by itself to get our final answer. So I can just divide both sides by the 3y squared and say that dy dx is 1 over 3y squared. But now that's a little odd that now it's in terms of y when it started with an x. So don't forget that now if we have a y in the problem, we can replace it since we know that y equals the cube root of x. So that can be my last step if I want to write it in terms of x, is replacing the y with the cube root of x. Now you'll see, even though it's written differently, that is the same thing as what we got up here. Because the negative 2/3 would just mean that x is in the bottom, and it has the second power and the third root. So this is the same as an x to the negative 2/3. So now that we've just done a small example, let's do a bigger example and see why you would really use this. So in this case, even if I wanted to, getting the y by itself is not really possible because I have a y here and I have a y to the third power here. It'd be very difficult. So I really do need to use the implicit differentiation, which means taking the derivative one at a time and remembering if I'm dealing with an x, it's what we're used to. But if I'm dealing with a y, I'm going to do the derivative and then multiply by the dy dx. That's the big difference. So for instance, this first term is similar to what we just did, where I'm going to use the power rule, but then times dy dx plus the derivative of this, since it just has an x, is normal. So hopefully you already know the derivative of 3x would just be 3. Plus, here we got to be careful because not only do we have an x and a y, but it's a product. So I still do need to do the product rule. It's just if at any point I need to do the derivative of y, I need to add that times dy dx. So let me talk you through the product rule. X to the squared as is times the derivative of y. So the derivative of y, remember, is dy dx plus y as it was times the derivative of x squared. So that's the product rule. On the right, derivative of 11 is 0. So hopefully you see the only thing really different from what we're used to is anything that involved a y ended up having this extra step at the end. So now, just like before, it's just going to be a little harder. We want to get the dy dx by itself to get our answer. So since two different things have dy dx, my first step is going to be getting both of them on the same side. So I'm going to leave this one where it is. I'm also going to leave the x squared dy dx where it was, but I'm going to move the 3 to the other side, which means subtract 3. And I'm going to move this, which is really 2xy, to the other side by subtracting it also. So all I'm doing is basic algebra now, keeping the two things that have what I want alone on one side, moving anything else to the other side. The reason you would do that is to now isolate the dy dx by first factoring it out since both of these terms have it. And then dividing by the 3y squared plus x squared to get it finally all by itself. So this is my final answer. So this is dy dx. So in this case, I don't have a nice answer for y, so I'm not going to replace the y's with something else. But it just depends. If you do have something where it told you that y equals something, then you can go ahead and replace it. But in this case, that's fine. So now for part B, it wants me to find the slope of the tangent line at this point. So it's giving me an x and a y, which is good because I have a place for both of those. So remember, anytime it's asking you for the slope of the tangent line, it really just means the derivative, just like always. It's just our derivative's a little fancier now. So if I have a point, I'm just going to plug the x and the y into my derivative. So I'm first just leaving space since there's so much going on here. And now I'm just going to carefully make sure I put 2 in for the x. So that would be there and there. And I'm putting 1 in for the y. Whatever all this gives me is the slope of the tangent line at that point, 2, 1. So -3 minus 4 gives me -7. 1 times 3 is just 3 plus 4 gives me +7. So my final answer is -1. -1 apparently is the slope of the tangent line at that point, 2, 1. So this is what you're going to do most of the time when using implicit differentiation. So now let's look at the other type, logarithmic differentiation. It's hard to say. So this is something you could do anytime because you're always allowed to take the log of both sides of the problem. It's just, why would you randomly do that unless it's going to help you? So when should you do this type? I would do this type if you already have the y by itself, because in this case, you could just do normal derivative rules. But doing that would be a big pain because you have a lot going on. Do you see we have all this to the third power times all of this being square rooted. So doing this straight, I'd have to use the product rule plus the chain rule for each of these. So it just is a lot going on. So you could still do that, but I'm going to show you now why logarithmic differentiation helps. Because if I do the log, or in this case, ln, remember you can do any log, but ln just is usually the easiest one to deal with. If I do the log of both sides, I'm here. So it seems like I made the problem worse. But the reason why this is nice is if you remember log rules, I'm now allowed to split this up because the log of any two things being multiplied can be split into the log of each one being added. So that's what's going to start making this easier to do the derivative. So I'm going to leave the left for now because I'm not ready to do derivatives yet. And I'm just going to rewrite this as nice as I can. So first step, I'm going to split up the two things that were being multiplied by adding the ln of each one separately, because you're always allowed to do that. That's one of the nice rules of logs. Next, I can make it even nicer by taking the exponents and putting it in front, because you, again, are always allowed to do that with logs, because that's going to make the derivatives easier. Since all of this is being square rooted, remember that's the same thing as all of this being raised to the 1/2. So I can pull that 1/2 out front. So now I've made this pretty much as simple as I can. So now I can do the derivative. Since I have x's and y's, I'm going to do implicit differentiation at this point. So how would I do the derivative of ln of anything? Remember, it's always 1 over that thing times the derivative. So in this case, since we're doing implicit differentiation, we got to remember that the derivative of y is dy dx. On this side, a number out front will just still be there, right? When you have a constant in front of something. But the derivative of ln, again, is 1 over that stuff times the derivative of that stuff. So I can just go ahead and put that on top. Plus, same thing over here. The 1/2 will still be there. But to do the derivative of this, it'll be 1 over that stuff times the derivative of that stuff. Not the technical words for any of this, but it helps me to do it that way. So where are we at now? I'm going to make this as simple as I can, and then I'm going to figure out how to get the dy dx by itself, just like we usually do. So I'm going to go ahead and distribute whatever I can distribute. I can go ahead and say plus negative 15x to the 4th, or I could have made that a minus. So maybe I'll make it a minus on my next step, just to make sure you see that you're allowed to do that. So the right is pretty much as simple as I can, other than the fact I could have said minus 15x to the 4th instead of plus a negative. So now what would I need to do to get the dy dx all by itself? All I need to do is get rid of this 1 over y. So couldn't I just multiply by y? And that'll do it. So same thing over here. So dy dx equals all of this. So I'm going to go ahead and make it a minus this time just because. So you can see that you're allowed to. If it's plus a negative, you could always instead just say minus. Times y. But this time, remember, we do know another way to write y, which will allow us to only have x's in our answer. So when you have that opportunity, I would always do it. You just make sure you put all of that together, because all of that's being multiplied by all of this. And most instructors will probably let you stop there. But that's the general idea of using logs in derivatives and why you would use them. So again, when it's a really complicated problem, and using logs will allow you to do this trick of splitting it up and even getting rid of the powers. Hopefully that helps. If you have questions, just write them in the comments and I'll answer as soon as I can. And I can always do extra examples if you need me to. Hope that helps.